All right, let's try that. Better? Okay. Yeah, sorry. I have to like mute this and not mute that. Okay, so for those that are watching, I was asking whether people wanted to take them. And it seemed like people would prefer take them. So let's do a take home. Good. Okay. Take it seriously though, guys. Just because it's take home doesn't mean it's not very serious. Yeah. Should probably do that with I'll do it with all three exams, like including final. I mean, I don't want to do one way and the other some different way. So, but that said, I don't want you guys to stop coming to class or like, coming in online. I want people to check out. So maybe I'll like some group projects. We'll like have some in-class things where, make it a little more exciting. Bring donuts or something. Huh? Bring donuts? Varsity? Yeah. Okay. Have some varsity donut experience in my life. Okay, guys. So let's recall last time what we did, at least where we left off. So we have this whole scheduling problem thing that we're trying to find a way. We have a bunch of tasks and we have a certain number of processors. We perform those tasks, what the optimal way to schedule these tasks is. And what we did last time is we talked about directed graphs as a way to help us model this situation. So let me just recall, because I kind of felt rushed at the end last time, what a directed graph is and some of the language that we have. So recall we called this a digraph. That's pretty normal. And we have sort of different names for things, although I might make the mistake of using usual graph theory, but or at least for the scheduling problems, I think they call edges will be called arcs. We have this thing called the arc set, which I didn't mention last time. This is just a set of edges. And maybe the difference with the digraph, I mentioned this last time, these guys are directed edges. So x, y is not equal to y, x. If I write x, y, that means that I've got a situation like this. X here and y here. And y-x is the opposite. Those are not considered equal, not the same thing. For directed graphs. You have the notion of a path. This is the sequence now of directed edges or arcs. I'll just say following the direction. And the last thing, which I felt really rushed with, was the idea of this finer sense of degree. We have the out degrees now and in degrees. The out degree is the number of arcs giving a point. A node, all vertices nodes. And in degree is the number of arcs terminating at a given node. So this is like, so you talk about out degree of a particular node. So I'll just actually won't draw that back. So Okay, so if I have a situation like this, um, this such a situation like this, then we have in degree x, 2, the number of arrows, arcs coming in, and then the out degree is 3. The total degree is still, if you just say the degree, it would just be the sum of these two numbers. Just a usual graph theory degree. So there's all kinds of models. I mean, we're talking about scheduling for this chapter, but there's all sorts of real life situations where you can use direct graphs as models. I mean, you can imagine if you're talking about a traveling salesperson problem or one of these sort of bridges type problems, one of these touring problems. You can imagine you have one-way streets or something like that you need to, there's a direction to the streets, so you can only walk in or drive in one direction. And then you want to put some directedness to the graph. Another example they give in the book is you could look at the World Wide Web. I don't know if people call it that anymore. Where you can say, okay, every single page, if it has a link to another page, then you draw an arrow going from that page to another page. And since that's directed, right? You can link to one page and then maybe you don't have a link. So there's a way of directing that graph, thinking applications to it. I'm sure that's quite used quite commonly, but I don't know. So for our purposes, for the scheduling problem, we want to talk about how we can use these directed graphs. And so we're going to talk about the project diagram. So we have some project with a bunch of tasks and processes and all that business. And the vertices are nodes are going to equal our tasks that we have to perform. And then the arcs are going to be precedence relations. So last time we had to give an example. Although actually I have to add one more thing. Sorry, let me add one more thing here. So this is all true, but we want to add actually 2 more nodes. We want to add a starting node and an ending node. We're going to add 2 nodes to our graph in addition to all the tasks. And then precedence relations, well, you want to go to, you'll go from the start to anything that doesn't have anything that requires to be, that is required to be done before you accomplish that task, and then end will be after all tasks that don't have any. Let me explain. Last lecture, we had this project, this group project example. And so the project, you and another student had to write 2 chapters of bibliography and an introduction. And you can only write the bibliography after you had in both chapters. So there were these precedence relations. this. And this would be, without my update, this would be the project diagram. We also had times on these. So when I draw this, I'm probably going to now start putting the time, the processing time for each of these in parentheses here. So we take 5 here. I think this was last time we did the processing time. But now we're going to add these start and end. So put the start to the left and to the right. We'll just, these don't take any time. There's just the beginning. And if there's nothing that is required to be done before a task, then we'll just draw an arrow from the start, an arc, start to that. So we'll do something, oops, like this. Okay. So this is our, this would be the project, oops, I also need to. There's nothing that is requiring a task after you're given a certain task, and you go directly to it. So you're done with the bibliography. Nothing requires bibliography to be, in order to be done, and similarly with the instructions, so let's just go directly down. But this will be an example of a project diagram for that particular problem. We want to use this in order to help us schedule the project. Although last time we figured it out, we kind of eye it, but in more general cases, it will work. Okay. Questions about any of this? This is actually kind of like, there's a lot of stuff in this one. I mean, I don't know. It seems like you've got these weird tables, you've got these diagraphs, you've got processing times. It's not like it's a little more nuanced, I think, than what we're doing before. But it's also kind of, and they only take it so far. So it's not too bad. Okay, so our next step to actually do some scheduling is to do what's called to make a priority list. This is the section 6.3. So we want to do priority list schedules. And it's really a simple idea. You just make a list of all of your tasks, just one at a time. The list of your tasks. This we call the priority list. So it should be a list, like in the sense that it's like I don't know, you go top down or left, right. It shouldn't just be like write each thing down all over, scattered all over the place. You want an order on it, that's what I'm saying. Okay. I'm going to give myself a little more room, guys. All right. So, question for everybody. Problem, question. If I have M tasks, or you have M tasks, I'll answer all at once. How many priority lists can you make? many ways can you make it? Question. Who has the answer? But you're fixing math.
Can you, so for like 8.2, homework? Like,
I don't know why. Yeah, I'm saying 6. This is like chapter. This is chapter 8.
Yeah. it is,
Like my
but,
notes.
Like 8.2,
Yeah.
like our homework is like a lot different from what. So,
Sure.
yeah, like it's asking about like cycles and stuff. Like it's asking like all cycles of 2, all cycles of 3. Like,
Okay, we can look at that. Let's do this, and what I'll do is maybe you can send me or talk to me after class and tell me which problem. I'm happy to do that. I didn't bring my book here, but I can take a look when we look at it tomorrow. Yeah, that'd be fine. Okay. Yeah, so I kind of skipped some language when I talked about the directed graph stuff. So there are like things like cycles, and I mean I talked about paths. A cycle, you're going to have kind of a loop or a circuit, things like this. So there's some language in the book that I haven't gone over, but that's because it's not actually. Whenever we have one of these project diagrams, we're not going to have any cycles. So since that's the only thing we're applying it to, I kind of didn't. But we can talk about some of that. Right. How about this question? Hello? No. Let's say you have 2 tasks. How many priority lists can you make? Task A and B. 2, right? So if I had 2, and B, I can make this list, or I can make this list. Well, here, I'll put them in. What if I had 3 tasks? 6. That's pretty fast. Did you like think of each one? Right. What are these called? What'd you say? Permutations. Right. Unbelievable. It's never happened for me before. One of my classes, I usually forbid that. Thanks. Right. That's good. I'm glad to hear it. So there's 6. So, and 6 is what? It's a number of permutations, but if I want to write 6 in terms of 3, or 2 in terms of 2, 3 flat factorial. 3 factorial. So the answer here, if I have m, is in fact m factorial. Right, that's the number of priority lists that you can make. So there are a lot of them if you have a lot of tasks. Even if you only have like 4 tasks, or 24. So you don't want to necessarily write down all of those priority lists. So I'd say the goal for this class and for this chapter is to really find a good one. Find one that could give us an optimal scheduling based on the priority list. So we have a little ways to go to get there, but the first thing we want to do is see if we write down a priority list, regardless of whether it's good or not, how do we then write down a schedule? How do we then make a schedule? So let's do that. Let's do that with this example. Copy this. Okay, so this was our problem before, and let's write down a schedule. Our priority list, pardon me, and see how we can get a schedule. So I'll do this sort of silly thing. I'll just say, let's try a schedule where we just go sort of in order. Write the introduction first. The chapter, first chapter, second chapter, third, and then bibliography. Okay, here I just wrote down a priority list schedule. I don't need to write down start and end. That's okay. Leave those. What I want to do again is I want to take this schedule and I want to, or take that list and then turn it into a schedule. So I'll write down more formally this process in a second, but let's just give it a try here. So I'm going to go from left to right. I'll start with the introduction and I'll see if I have, I'm starting at time 0, so I'll see if I can schedule it, and I can because nothing is, you don't require anything to be done in order to do the introduction. So I'll just schedule that. Okay, I've done that. I'll cross it off so I don't lose track of where I am. The first, so second student is free. First chapter needs to be written. Nothing is required in order to write the first chapter. So we'll assign this first chapter to the second student. Then we go on, so we scheduled that. Next in our priority list is the second chapter. I'll look at the available time as the first student is available at time 3. So I can schedule that, put that here. And now I've scheduled that and I look at the bibliography. However, so the second student is available at time 5, right? Second student's available at time 5. So I'd like to be able to schedule something for the second student. However, when I look at my priority list, the only thing really that needs to be scheduled is the bibliography. And that can't be done until both of these chapters are complete based on this part of our graph. So we have to wait. And then we have to wait until 9, and then both students are available. So I guess, you know, I've always thought, I don't know about you, that the first student is smarter. Let's give it. Right. No, I'm just kidding. I don't know any of these students. The students. Stop being smart. You get scheduled one. What's that? Oh, come on. They're geniuses. Future of the next generation or something. All right. So this is the way this works. Now I could have put in, there was no right here. I mean, I could have certainly scheduled the second student with the bibliography. There's no, you have some freedom to make a choice. If you're at a particular time, more than one processor is available, you can just kind of decide. That won't affect the time. So this is clearly not, based on what we looked at last week, an optimal. So not optimal. Right, we don't get the best time here. It takes 11 hours to complete the project. And so the point here being that if you just randomly write down a priority list, you're not going to, you know, you're not going to do the best as good as you can. So part of the problem is finding a good priority list. I mean, that's sort of the main problem. Okay. So let me formally write down sort of the algorithm to do what we just did. Normally, here's the instruction set for the priority list schedule. Priority list schedule. What do you do? So first, is that all processors, if all processors are busy, you have to wait. So the thing you're looking at here, this algorithm, is the time. So if we look back at this one, we'll start at time 0. No processes were busy at time 0 when we started this process. So we don't have to wait. But after we scheduled, let's say we scheduled the introduction, we scheduled chapter 1, and after we scheduled chapter 6, you could have said, okay, well, I'm going to go to time 4. Everyone's busy here, right? Processor 1's busy with chapter 6. Processor 2 is busy with chapter 1. So, sorry, processor 1 is busy with chapter 2. Processor 2 is busy with chapter 1. So you wait until 5, and now processor 2 is available. So if all processors are busy, you have to wait until the next time. Now, if one processor is free, then you'll give the next ready task to that processor. Okay, so it may turn out the way you've written your priority list, I shouldn't say the next, say first. Sorry. That's first. So it may turn out the way you've written your priority list is that you have to skip, because of the precedence relations, you have to skip some tasks that you can then become first later. So each time one of the processors is ready, you have to look at that list, and then the first one on the list that is ready to be done, to be completed, goes to that processor. So each time a processor is available. And then if more than one, if at a particular time, if more than one are ready, I think it's ready, I say free for processors and ready for tasks. And you can choose, so just give the ready tasks one at a time. You can choose which one goes where. Oh, I should say first ready. So we'll try again. We'll do this again with this more complicated example and have 3 processors here. To make priority list. So let's move this whole thing. All right, so let's do this as an example. It's hard to get it all on the screen here. So in order to do this example, we need a priority list. Okay, so we have A, B, C, D, E, F, G, H. Sorry. what should we do? Let's go opposite of alphabetic. Now this is like. So I'll just go backwards. Here's a list. HG F. Two, G1, D3, 2. So confusing. These are all like chess squares. Guys play chess? Anyone play? No. No chess? No players? Good. All right. Good. Okay, I have a job for you then. Hard to get Manhattan to play chess. So I go to my daughter's elementary school. Run their chess club there. They're fun. Kids are fun. I need more people to do stuff. Huh?
Smart.
Smart. They're like 8. I don't know if they're smart. You can determine that until they're older. Just they're ridiculous what they are. They like, I mean, they're afraid of my daughter. As they should be. On the chessboard. Like it's not like to beat the kids up. Okay. So what do we do, guys? Talk about the algorithm. What do we do? So we're going to start at time 0. Start at time 0. We look at, are all processors busy? No, none of them are. So we're actually in this situation. More than one are free. All 3 are free. So we have to look at our priority list right here. And we have to find the first available task. What is the first available task? Our first ready task, I should say. Going left to right. First ready task. Tell me. Is H3 ready? Task H3 ready? H is all the way over here, and in order to do it, I need to have done E before I do H. So H is not ready. It's ineligible if we want to use their language. It's not ready. So I want to look for the first ready task. G, which should be 2, sorry. 2, that's not ready. Is F ready? E, I need to do these 2. D is not ready. How about C? C ready? C is ready. Only thing I need to, I've started. So I already started. So I can put C in there. Regret this. Probably regret this. Let's not. I'm going to copy this first because I think I'm going to do another. All right, so C is ready. So we're gonna do C. And we can give it to whoever we want. Let's give it to the second processor. Now we're still at time 0. We have more than 1. So now we look at the next, we'll cross this off. Look at the next ready task. What's the next ready task? I'm sorry. Okay, so which one? You're right, they're both ready. So the only tasks that are ready at this point are A and B. But which one are we going to assign? B, right? Because this is a priority list, which means this one takes top priority. This is second priority, third priority. The priority list left to right is what's taking priority. So then it doesn't matter in this particular case, but in other cases, it would matter. So I'm just saying, right now, B takes priority. That's the one that we're going to assign to one of the processors. So we'll do that. And again, I've got two processors free, so let's give this one to 1. And now A is the next ready one. So we'll deliver A to processor 3. And now we're going to, okay, so we've made all of the assignments at that particular time. We're going to take a step up in time, go to time 1. Okay, these guys are busy. They're doing their tasks. However, the processor 3, that guy is not busy. So we can assign a task to him. So, or at least in theory. So can we assign a task to him? This particular time, can we assign a task? No, why not?
Because B2 is not done and that has to be done.
Right. So what you're saying is that all of these tasks that are on my priority list now that I've crossed off these guys are ineligible. None of them are ready. So even though P3 is done, with its task A, right now there's nothing, there's no eligible, or there's no ready task. So we just have to do some idle time. I'm sure I wrote that as in the algorithm, but yeah, if there's nothing ready, you have to wait. So now here, we got processor 1 and processor 3 are ready at time 2. Can we assign either of them a task? You could assign what? D? Yeah, I can assign D, right? Because at this point, B and A, they've been completed. So D is now something that can be assigned. So I can assign D, and again, you can choose, if you've got more than one processor available, you can choose either one. So we'll choose assign D. Let's go to the first. Again, now I look at the second guy, I look back at processor 3, he is available, or she is available, or it is available. Either one. Do we make an assignment? Is there anything that we can do here for processor 3? Like out back having a smoke. Oh,
C is not.
right. Right. E is not available, it's ineligible. Because C is not complete yet. And of course, F and G, they require D to be finished. So we're going to have to just tell processor 3 to have another smoke. Idle more. Don't smoke. Okay. Now we're at time 3. We got a lot of, all 3 of them are available. Can we make assignments? And if so, sorry, I didn't cross off D. If so, what can we assign? What should we assign? Okay. E. Sorry, it's the first one, is it? I need to assign a task, so I look at the priority list. Right, I have to start here. That's ineligible because I haven't, because I have not completed E. G is ineligible because I haven't completed E. However, both of these are eligible. And F occurs first. So I have to assign F first. I'll do that. We'll assign F just to the first guy. And now I can assign E. And again, In this particular example, it does not matter, but in other examples, that ordering would matter. So now we'll go look at the list, and I'll assign E. And I can look, and again, and processor 3 has got a lot of good race. Processor 1 and 2 are gonna like. Call their union rep or something. This is not fair. So these guys have been assigned. We can look. However, yeah, again, we have idle time here because the only things available are G and H, and both of them require E to be finished. Our next time is for processor 1. We could look, and processor 3 again. They're both available. They can do stuff. However, again, in order to do G or H, we need to have finished E, and E is still going on over here. So that's no good. So we have to wait until time 5, and then we can assign first H and then G. We wait till time 5. Now we have all 3 open. And so we can assign H. And then G. We'll give processor 3 all the time. Processor 3 is in the hospital for fun. Okay. This is a schedule. So question. So the processing time of this schedule is what? What people say? 8, right? Processing time of the schedule is when we finish. It's 8. Question, can we do better? Probably. There's a lot of free time. We do better. Say no? Why not?
You wouldn't like the priority of the list.
Huh?
We wouldn't select the priority, like we went through the list.
Okay, but as I said before, when we looked at this, we did this before. We did the priority list up here. This is not the most efficient, right? This is not optimal. And in fact, we could have sort of, if we had just switched chapter 6 with I, it would have been faster. Or maybe, yeah, we would have been able to assign the introduction to this guy and then made it faster. So just because we're following correctly, even if we're correctly following the priority list, doesn't mean that we're going to get an optimal schedule. And that's because, but there will be some priority lists where we will get. So the challenge is to find a good priority list. However, in this case, it is indeed optimal. This is an optimal. It's not fair. I mean, if you're processor 3, it's optimal. But if it's not, fairness has nothing to do with it. It has to do with how long, what the processing time is. So this is optimal in that sense. In other words, you can't do it any quicker. You could be more egalitarian and make better assignments. Why is it optimal? Let's spend the last 3 minutes or 2 minutes thinking about that. This is something that's a couple of sections ahead, but we'll get to it. I don't know, probably next time. Right. Okay, so that's the right idea, is that we do, these tasks have a precedence relation. So we are going to have to wait for certain tasks. But why 8? Why 8? So part of this is looking up this graph, looking up this graph. This graph will help us sort of determine sort of the lower bound for how long for the processing time. It will give us a lower bound. So for example, let's say we have D1. Let's look at task D1. How long are we going to have to wait before we do D1, and even the best case scenario? Out 2, because it requires these 2 tasks. So maybe at one process, they can be done at the same time by different processors, but it will, you're going to have to wait 2 hours because B takes 2 hours. And then F, you're going to have to wait, well, this 2 hours, you're going to have to wait the 1 hour of D, and then you'll have to wait 3 hours before you do that. So if you look at the following path, you think of this in terms of end, your ending. How long do I have to wait to the end? Well, I'm going to have to at least wait. I won't be able to do E2 until C3 is complete. I won't be able to do H3 until E2 is complete. I won't be done until H3 is complete. So H3 requires at least these tasks and then some others, but at least these tasks to be finished. So you're going to have to do 3 hours, then 2 hours, and then 3 more hours at least until you're done. And so the sum there is 3 plus 2 plus 3, which is 8. So that says no matter how you schedule this, it's going to have to take at least 8 hours. And since we found one that does take 8 hours, it's optimal, even though it's not fair. So we'll see that that path I just drew is called a critical path. We'll talk about that either next time or probably next. All right, guys, have a good Thursday. See you on Friday.
For a second.
Yeah, I got a little carried away. That was